ChatGPT. Ok. C'est globalement l'architecture ChatGPT. Enfin, c'est pas la version de chatbot, mais on verra un petit peu comment ça fonctionne un GPT, donc pas un ChatGPT. Mais donc pour l'instant, on va faire sur les réseaux de neurones récurrents. Et le prochain cours, je crois que c'est vendredi. Donc le traitement du langage naturel, c'est la compréhension du langage. Alors, et je dois pas le faire en anglais, hein, tout le monde parle français?
C'est enregistré. Et ceux qui
Ah,
parlent
ok.
français.
Okay, so I'll do it in English. So we are going to talk about recurrent neural network for natural language processing. So natural language processing is the understanding of human language by algorithms. So it includes text understanding and text generation because these two tasks can be different. And we're going to look first at words and sentence embedding. So that's basically the understanding part, because it's basically how to transform some words or some sentences into vectors, because the algorithms that we use, they cannot understand words. You need to vectorize them so that they can compare them. So because you can put a distance in a vectorial space. So here you have an example on the screen. You can see that in a good encoding space, if you vectorize the word newspaper, you get vector. You vectorize the word magazine, and you vectorize the word biking. The goal of our network is to have the words that have a similar meaning needs to be close together in the vectorial space. So here, newspaper is close to magazine, and biking is far away. So that's basically what we're going to do first with a non-recurrent neural network, and then with recurrent neural networks. So it's written reminder, but I think it's not a reminder for you. Here I'm showing the two instances of the word2vec algorithm. And so the word2vec algorithm is trained. So it's an algorithm that is trained to find missing words in a sentence. So on the left part, you have the SIBO algorithm. It's for continuous bag of words. So basically, you have a sentence of, let's say, 5 words, and one word, the central word, is missing. And the goal of the algorithm is to turn all the non-missing words into vectors, to sum them or to average them. And the sum needs to be close to the encoding, the embedding, the vector of the missing word. So I'm going to use the term encoding and embedding. So basically, it's the fact of representing words as a vector. We can call it embedding, and we also can call it encoding. I'm not going to dive into the details. And for the skipgram part, the algorithm is trained to find the 4 missing words in the sentence given the central one. So it has to guess the surrounding of a word. And so, of course, it can be 4 words, but depending on the parameter that you have, you can say I'm going to input 3 words, 5 words, whatever to the network, and it's going to have to find the missing ones. So I'm detailing here the architecture. So basically, you have a dictionary of words. So let's say you have, I don't know, the example is 10,000 words. So your algorithm can encode 10,000 different words. And each word is represented in the input vector as a position in the 10,000. So let's say that, I don't know, the word ant might be the 10th one of your dictionary. So the input vector for the word ant would be zeros everywhere, apart from the 10th position, and it would be a 1. And this huge vector is going to be inputted to your network to reduce the dimension and make it more meaningful. So basically here, if you would want to work with the 10,000 words, you would have no idea how to compare the words, because each vector would be orthogonal to the other. So for instance, the 9th word would be able, I don't know, and able would be as distant as ants as any other words in the dictionary, because all the dimensions here are orthogonal, are different, and so you cannot compare the words in the input vector. So the goal of your network is to create a vector, a vectorial space in which you can compare different words. So you have, I guess you're familiar with neurons and stuff, right? You've seen some of them before. So basically, you have two layers of neurons, and the central one is going to create the embedding. So what you do is you input the vector for your word to the network, and it's going to create with the neuron a 300 dimension vector for this input vector. So it reduces the dimension. And then, so let's say you have a SIBO. You do that for the 4 words in your sentence. So you get 4 vectors of 300 dimensions. And then you sum them or you average them. And then you have another layer that projects these 300 dimension back into the 10,000th vector. But instead of having all zeros and 1 at the right position, it's going to be more continuous. So you're going to basically have a probability distribution over all the 10,000 words. And basically, the most probable word would be the word that you guess. So let's say your sentence is, do I have an example? Yeah. So let's say your sentence is, this is a visual comparison. So the word that you have to guess is visual. So what you want here is to project is comparison and this into your 300 dimension, make the sum or the average. And then you want your network to predict a probability density that has its highest value on the position of the word visual in your dictionary. Is that clear? Okay. And so by doing so on like with millions of sentences, in the end, by the statistic distribution of words in sentences and the fact that some words come often with other words in the same sentences and stuff, you're going to get a meaningful embedding space. So for instance, here, a newspaper is close to magazine. And that means that in all of the millions of sentences that the network has seen, when it has to guess a missing word, basically magazine and newspaper are going to be almost equivalently probable, let's say, because they are often in the same group of words as each other, basically. And so here you have a bigger visual representation of a word2vec embedding. And so you can see, so of course it's like 300 dimensions, but you can project on 2 dimensions to visualize. And you can see that you have similar meanings to neighboring words. So for instance, if you zoom on the surrounding of the word see, where's my mouse? Okay, on the word see, you get so many C-related words. And so that means that our network has kind of worked and extracted meaningful vectors out of the words it has seen and the task it had to do, which was to guess missing words in sentences. So, so any question here so far? Okay. So the problem with word2vec is that it can create embeddings for words, but the embedding for the sentences are going to be hard to get. So in an ideal world, you would want to be able to vectorize sentences in the same vectorial space and compare the sentences. And here you have the example of a sentence about a lion, another one about a tiger, and both are close together because their meaning is related, let's say. And the third sentence is further away because the meaning is not related. The problem with word2vec would be that if you take each word embedding and you concatenate them together, you would get vectors for the sentences that have different sizes. for instance, the last sentence would have 4 times 300 dimension, and the first one would have 7 times 300 dimension. And so they wouldn't have the same number of dimension, and you wouldn't be able to calculate the distance between the two, because it's difficult to calculate the distance between vectors that don't have the same size. Anyway, so that's why we're going to introduce a recurrent neural network. So recurrent neural network are made broadly to work with sequential data, but originally more in NLP, but now you can use them in so many applications. And so what is a sequential data? So if you recite the alphabet in your head in the right order, that's going to be easy for you, right? If you recite it backward, it's going to be way more difficult. And if you start from the letter N, you're going to, you know, have a bit of difficulties maybe in the beginning, but that you're going to be fine. And so it means that you have learned the alphabet as a sequence. And so, yes, you probably don't read backwards, and your brain takes a bit of time to retrieve the sequence when it's not starting from the right letter. And we're going to basically create an algorithm that has the same kind of behavior, which means it knows, it will know the language in a sequential way, which Word2Vec does not do, right? Because Word2Vec averages some embeddings here. If you Word2Vec makes the average, and so it's not sequential. If you change the order of the words for Word2Vec, it's basically the same. And so we don't want that, because we want to understand the language as a sequence. And so sequential data can be many kinds of data, right? It could be video, audio, and here we're going to work with text. And it's super important, especially in the language, because well, the meaning of the words depend on the context, and it's not fixed, right? So it will depend on the understanding of the words that come before. So for instance, if you say I like fish and chips, and if you say these chips can out-compute modern computers, obviously chips don't have the same meaning. And also, if you have the sentence, the car fell from the boat and the boat fell from the car, it's a different sentence, right? With a different meaning. But for Word2Vec, it will be the same, because the order doesn't matter. So that's why we want to work with sequential data. And so we need an algorithm that can process this kind of sequence. So as I said, sentences, they don't have a fixed size, so we need to find a way to deal with that. So we need to find the right size of the embedding for a sentence. And so in Word2Vec, you can say I'm going to average all the words of the sentence. So I have, let's say, a sentence of 4 words. I'm going to average the vectors of the sentence. It's going to create a vector of 300 dimension, right? But then like the order won't be incorporated in that representation. And so different sentences can have the same vector and don't mean the same thing. And also maybe due to the geometry of the vectorial space, some information are going to be lost if you create the mean of all the words in the sentence. So that's not good. But as I said, if you concatenate all the words embedding, you have a dimension that is not fixed, so you cannot compare the different sentences. And also you cannot train a classifier, because I don't know if you've done classifiers yet, but classifiers has an input dimension. And so if the input dimension is not fixed, then you have a problem. And so that's for the understanding part of the language, let's say. But if you want to generate some sentences, your algorithm need to have a way to stop. And it's not like the right solution would not be to make all the sentences the same size, right? You say, okay, generate, let's say 5 words, and then all your sentences have a 5 word long. That's not good. And so we also need to have like a stopping condition of our algorithm. So we're going to see that. I just want to say that in the notebook, we're going to have a fixed dimension for the output, but that's just going to be for engineering matter because designing, like practically designing the algorithm to not have a fixed dimension is going to be complicated. So we're going to see the theory here, and in practice, we're not going to do it. But that's what you should do anyway. Okay, so the recurrent neural network are going to be our first solution. We're going to see the transformer network on Friday, which are going to be the state-of-the-art solution, you see. And so the recurrent neural network are used in many applications: speech recognition, NLP, stock prediction. You could also do it for image processing. I might dive into that later. And so it's a very broad way of functioning. So what you're going to learn here for language can be then applied to other sequential data and even non-sequential data like images. All right. So a recurrent neural network is a network that is going to sort of loop on itself until it reaches a certain stopping point. In order to understand sequential data or to generate sequential data. So if you, for a standard neural network, you would have an input, you would have some hidden layer of neurons, and then you would have an output. So for instance, you have a classifier, let's say, you have an input image, and then you have your convolution or whatever, and in the end, you classify whether you have a probability that the image is a dog, the probability that the image is a cat or something, right? So that's not recurrent, that's just a standard one. And when it's recurrent, it's going to basically use some internal information to loop on itself. So typically, you would have several words, and you would pass information while reading the second word. You would pass information from the previous word that you read in order to better understand the second word. And then to understand the third word, you would have information passed from those two previous states, etc., etc. And so basically a recurrent neural network, it's an artificial neural network that functions as a temporal sequence that displays dynamic behavior and that can process variable size input. So it's going to loop through what we call a hidden state. I'm going to dive into that. That's basically a vector that is passed on from state to state. It can or it doesn't really necessitate new inputs and does not always generate new outputs at each time step. So we're going to see that as well. And it's very efficient, obviously, at processing series because it was designed for that. Yes. Can I? Okay. So we're going to see some example of processing sentences. So our goal would be to compare different sentences. So here, so the task would be to generate, let's say, an encoding for each of the sentences. So I'm going to simplify a bit the task because here it's a bit blurry, let's say. We're going to have a simple example of classification of text. And basically, our toy task would be to classify whether a sentence is about asking for the time or asking how someone is doing. And we're going to review how the RNN is going to classify the sentence, what time is it? So I think you've seen that in the previous classes. So that would be tokenization. And it's basically turning the sentence into a series of what we call tokens. So it could be words and punctuation, but it can also be more complicated than that, radicals and end of words. But anyway, so here our tokenization is super simple. It's each word is going to be a token. And this token is going to be turned into one hot encoding, as I've shown in the beginning, like a vector with all zeros and a 1 to the position of the word in the dictionary. And this input is going to be fed to the network. And so the network is going to encode like a standard word to vec. Let's say it's going to create a vector for the word what. And actually, the output here is optional because the network doesn't have to do anything yet. So it's shown that actually there is no output. However, the encoding vector, let's say, of watts is going to be passed to the network so that it has two inputs, the previous encoding of the previous word, and then the word, the vector for the word time. So it's going to create a new vector. So it's a black box for now, right? So it's going to create a vector that assembles in its own way the previous hidden state and the encoding and the vector for the word time. And then it's going to pass it on to the third step. And so the third step would be the same network receiving a different hidden state that incorporates the two previous words and also a new word. And it's going to do that for all the tokens in the sentence, so that in the end, it generates a vector based on the hidden states that represents all the previous words in the sentence plus the last word. And then we're going to use only the fifth output, which could be, let's say, a new vector that we have decided to create in a certain way, or just the raw last vector that has been created, this one. And then this final output is going to be passed on to a classifier. And the classifier is going to say, okay, this is not a sentence about asking how someone is doing, but it's a sentence about asking for the time. Right? Any question? So here you have a pseudocode of it. So it's like, it's not really like it's a simplified Python, let's say. So so basically you have a network. On top of that, you have a classifier, which is the feed-forward network. So you have an RNN that you have defined in a certain way. You have a classifier that you have defined in a certain way. You have a first hidden state that you initialize. So it can be all zeros. It can also be random, but let's say it's all zeros. And for each word in the input, you're going to create a new output and a new hidden state based on the previous hidden state and the new word. And so it's basically a loop on all the words in the sentence that you pass through the RNN with the hidden states. So either the first one, which is all zeros, or the previous one generated by the RNN. And then you take the last output and you make a prediction with the classifier. So this was a very simple task. And usually to train a recurrent neural network, you don't train it on classification because classification is a sort of a discrete task. You have a number of classes, 2, it can be 1,000, whatever, but it's still discrete. And the embedding that is generated by that kind of task is not super useful, especially in text. So for image, the classification task could be good because on the visual dimension, you have to basically recognize object. That's what the vision do. So if you have many classes of object and you train a network to recognize the object, it's going to generate meaningful visual encoding. But for text, that's not text is not used to classify objects in the human brain, let's say. And so classification is not a super good task. So the most common task would be encoding decoding. So that's basically turning a sentence into a fixed dimension vector and then turning this vector back into the original sentence. And that will allow the encoding the vector to keep all the informations of each word, because the sentence has to be reconstructed from the vector. And so classification in the context of natural language processing is often used to fine-tune a pre-trained model. So that means that you train your model on an encoding decoding task, and then you want to classify something. I don't know, you want to classify spam, for instance. Well, if you train your network only on this task, it's going to have very poor representation of each sentence. But if you train it first on encoding, decoding, and then you only fine-tune the last layers on the classification task, the results are going to be way better. So I don't know if you're familiar with fine-tuning, are you? So basically, fine-tuning is when you, after training a network on a lot of data and a super general task like encoding, decoding, you're gonna basically freeze most of the neurons, most of the weights of the neurons in your network. And basically, only some of the last layers are going to be trainable. And you're going to train the last layers on another task, the task that you want to accomplish, basically. And that is called fine-tuning, because it's not training from scratch. It's just moving some weights in order to be more precise on a specific task. And so now that I've explained roughly what is a recurrent neural network and how it works, we're gonna see how to train it on an encoding decoding task, which is a bit more complicated. So as I said, encoding is when you transform a sentence into a vector of fixed size. So that's what we saw well, we saw that in previous examples. And then decoding is regenerating the sentence from the fixed size vector. And so it's done through autoregressive generation in the end, and the encoding that we just seen. So the encoding part is very similar to what we've seen with the what time is it sentence. And the autoregressive generation is when you generate an output based on the previous output that you generated. So basically, you're going to be recurrent, but in the generative domain, you're going to generate a word, and then the second word that you're going to generate is going to be based on the first word that you generated. And then if you have generated n words, the n plus 1 is going to be based on all the previous words. But as in the encoding part, the step 1 is initialized in a certain way. Right? And so you could do simple encoding decoding in a fixed language, right? You could also do it in several languages. So you could encode in a language and decode in another. That would be, let's say, a more difficult task and maybe more meaningful for the network. So here I'm going to show you decoding parts in probably Spanish, and we're going to see that it's linked to an encoding part in English. So the whole task would be translation, basically. So for now, only autoregressive generation. So you have to start to tell your network to start. So it hasn't generated any word yet. So the first word that you input the network is a token that represents the starting point. And then it generates a first word. So the first word would be amo. And then as it generated a word, you can input it to your network in order to generate the second word. But you can also input it a hidden state. And so what you can do, like with the encoding, you can have a recurrent neural network that has a word as input, which is the last word generated, and a hidden state as input, which represent the previously generated words, and also in the case of decoding a vector, the original vector. So yeah, any questions for the decoding task? So the full task would be encoding, decoding. So it could be in the same language, or it could be English to English. That would be already a difficult task, but it can also be English to Spanish. And so you have basically an encoder that encodes sentences as we've seen with a recurrent neural network. It generates a fixed size vector. And this fixed size vector is not going to be used to classify whether the sentence is about whatever. It's going to be used as first hidden state of the decoder, basically. And so the decoder is going to loop on itself, generate words that are going to be inputted to itself, and also pass on a hidden state that is going to incorporate the original vector plus all the previously generated words. So the full architecture would be this. You have a sentence that you input your vector, and you don't care about any output for now, right? So the encoder and the decoder are two different neural networks, right? They're just both recurrent, but it's not the same network, just to be clear. So you basically pass on the hidden state. You add new words until you reach the end of the sentence. And the last hidden state, or custom outputs as well, you could choose, can be used as a vector representation of your sentence. And then this vectorial representation of the sentence is going to be fed to the decoder as first hidden state, which is going to generate a word. And then to generate the second word, is going to take the previously generated words and the new hidden state, generate a new word, and then it's going to take this new word as input plus the hidden state generated by the previous step until it reaches, until it generates basically a token that signals the end of the sentence. So as I said, in our example, designing the end token is going to be a bit complicated. So we are not going to do it. We're going to tell our network to generate fixed size sentences just to make it simpler. But in theory, a good network needs to stop by itself, because obviously, for instance, when you translate or when you reconstruct a sentence, it cannot be always the same size, and you cannot fix the size in advance. I just want to say that you can train pure encoders and pure decoders. So it doesn't have to be encoder decoder all the time. So we saw a pure encoder. So it was a shitty one, but anyway, it's still a pure encoder. And you can also have a pure decoder, which would be something that finish your sentence, for instance. And this network doesn't really need to have a fixed size embedding at some point, or it's hidden, because it only needs to generate words. So it used to be more impressive than that, but now ChatGPT is here, so it's less impressive. But basically, with this page here, you can input the beginning of a sentence. So if you have any, can you complete? So I am thinking what? Me, okay. Well, I'm not teaching you then. Anyway, that's a bit lame, but you can see that you have something that finishes your sentence, and it never uses it doesn't use an embedding. So if you want to play with it, you have the link in the, you have the slides, right? So you have the link, but anyway, it's way less code than ChatGPT, because ChatGPT, the free version is based on GPT 3.5, I think, or something like that. Here is GPT-2, so it's super old. Yep. So can I go back to, please can you move? Yes. Okay. So basically here it's going to be a bit more technical, maybe. So we're going to see how the network is going to be trained, because we've seen the task in a global setting, but we haven't seen how the network really learns to update its weights. So we're going to see it here. So basically, I think I'm showing it for only one sentence. but actually the network is going to be trained in parallel with several sentences. So anyway, here we're going to see how to train it on one sentence and to make it a better predictor, a better reconstructor of the sentences it has encoded. So for the encoder, it's actually quite easy because there is only one task, let's say, and the task would be to create a vector representing the sentence. But for the decoder, the task is going to be a bit more difficult because you don't train it to predict the full sentence like at once. You train it to predict the next word in a partial sentence. So in this example here, it has encoded the sentence into a fixed vector and is trying to reconstruct it. And it already has generated 2 words. And you want it to generate the third word. And so you have to compute the error it makes on that step, but you do it for every step, basically. And so it's not one error that you calculate, but an error for each word in the sentence, for each step of generation, basically. So that's it. Maybe I don't know. Anyway, maybe I'll dive into the details later. The problem with that training, let's say, for a simple neural network, is that if the sentence becomes too big, basically the full meaning of the sentence starts to dissipate during the encoding. And at some point, the contribution of certain words are going to fade out during the training. And so if your training steps at the end of a sentence, let's say you're trying to predict the last word, the meaning of the full sentence has dissipated, and the first words of the sentence are diluted in the embedding. And that means that the error that you're going to calculate that might be on a word in the beginning of the sentence is gonna be kind of wrong. The error is not going to be like the way you tell your network to improve is not going to be great. And so that's a problem that we're gonna tackle just after. So anyway, if you have a really big sentence, and let's say you're trying to predict the verb here, and the verb is related to the man here. And so if you make an error on the verb, actually, it might be that the representation of the word here was wrong, but the error that on the embedding that you're gonna calculate is going to be an embedding, a hidden state that has passed from man to who, to war, to a, to weak, to on, to his, to ed, and to went. And so actually the error that you calculate is gonna dissipate. And so that's the problem. Like a visual representation of that would be from our previous example. You can see that when you have the embedding of the beginning of the sentence of what time, you can see that basically the encoding is half-half, right? What and time contribute for half of the sentence. But as you progress, basically the last words is always half the embedding, sort of, and all the rest of the words are the other half, which means that well, it dissipates basically, and so the information is fading away. Yes. And so I'm summing up what we've seen now. We've seen that the recurrent neural network is great to model sequence of data, and because each sample is dependent on the previous one, and it can loop on itself. The problem that we've seen, I mean, experimentally, that you can see with a standard recurrent neural network, is that the gradient, so the gradient is basically the error that you calculate. The error that you calculate is gonna fade out in some long sequences, and it's the error that you calculate is not gonna be good to improve the network. So there is a solution to that, and we're gonna see it because it's super common. So it's basically improved recurrent neural network. I'm not going to dive into the GRU, which is gated recurrent unit, but I'm going to dive into the long short-term memory network, LSTM, because they are interesting. Oh, that's the not advanced version of it, probably. So maybe I'm not showing it to you. Maybe not. Or maybe I don't know. Is it bugging? Is it masked? Yes, okay. Yes, I masked this slide. So anyways, you should know that the solution to that is a specific kind of network. If you have questions about them, I can show them to you. But I think we're gonna rather manipulate them in the notebook rather than having a big fancy theory that you might not want to use later. Anyway, so if you're curious during the practical session, if you ask me some questions, I can go back to LSTMs and GRU, but I think we're gonna move on to the notebook unless you have questions. Online, do you have questions? No, you don't. Okay. So was everything clear in English? Because I can also answer questions in French. Okay. And so I'm just gonna send you you probably have the link of the notebook. So you should go check it, and yeah. So for the notebook, yes, you should modify the type of execution here to have a GPU. All right. And then you can basically run the notebook. Yes, probably you need to make a copy of the notebook. Okay, so you first need to create a copy, and then you need to change the execution type here and use the GPU, right? Okay. All right. So I'm going to present what the notebook is about. I'm going to let you look into it by yourself a bit, and then I'll catch up so that you have a bit of time to read what it's about. Yeah. So we're going to do two things in this notebook. We're going to train the network as a sentence encoder, and we're going to use this RNN to do sentiment analysis. So it's going to be predicting whether a movie review is positive or negative. And in the second part, we're going to train the recurrent neural network as decoders, as pure decoders, and use them for automatic text generation. Yes. Well, I'll let you read a bit and catch up. And I'll catch up. Après, tu sais, tu fais mage entrée. Sur une cellule, tu passes à la suivante et tu veux. Je vais peut-être le dire, si les gens savent pas. Okay, so just so you know, you have some tools with the notebooks. So here you can execute all the cells. So it's going to run all the cells in the right order. If a cell bugs, it's going to stop. So, I mean, you need to have all the cells that are working. If you have a problem with the cell, it can be that, I don't know, a library is not up to date or something has changed in anything. And you tell me and I'll help you deal with the bug. But normally everything works. And then when you're on a cell, if you press Shift plus return, ou maj plus entrée in French, it's going to run the cell and go to the next one. So if you want to run cells quickly, I'm doing maj entrée and it's running the cells, you know. Anyway, I'm not connected, so it's going to take time. So I'm gonna explain what it's about. So you probably in the last practical session used NLTK. I'm not sure, but it's basically a toolkit for natural language processing. It helps you easily separate the sentences into tokens and some other stuff that you probably have seen in the last session. And then you have a lot of other libraries that you might know if you know Python. These libraries for random numbers. This library is to work with text, basically. This one is to plot some graphs. This one is to deal with arrays. This one is to deal with some data frames. And then you have some NLTK. This one is to compute some metrics, basically to measure the performances of your networks. Torch is a library to create neural networks. So I don't know which one you've used, but basically there are three main libraries: Torch, PyTorch, but it's imported as Torch, and you have TensorFlow, and you have then like a library that is based on TensorFlow, but that is much simpler, which is called Keras. So maybe you've worked with Keras, but anyway, here we're going to work with Torch because it's the best one. And yeah. So when you have a computer and you want to perform deep learning calculation on the GPU, so the graphical unit of your computer, you need to have a specific library which is called CUDA, that is designed and supported by NVIDIA, basically. So I don't know if someone told you that, but basically when you do deep learning calculation on a processor, on a standard processor, it's kind of slow. And the graphical units that were originally designed to compute graphical calculation, so for instance, video games, they can do many calculations in parallel. And it's actually super efficient for deep learning. So most of the deep learning, like if you have a big network, usually it's trained on the GPU. And so if you have a gaming PC, you probably have a good PC to do deep learning. Anyway, so you need to this is the device on which you're going to make the calculation. And so if you have enabled the GPU on your notebook, as I told you to do, normally the GPU is available, so the device is going to be CUDA, which means do it on GPU. And if you didn't enable the execution, it's going to be on CPU, but you might have very slow calculations if you do that. So here it's a bit of code to download the data from IMDb. So it's a movie database, right? And we can then pre-process the text. So we have several parameters, but anyway, so you've seen that NLP network has a dictionary of known words. So if you have 10,000 words, then you have a dictionary that is used as input, and you have each word as a position in the dictionary. And when you input the 10th word of the dictionary to your network, the vector is going to be all zeros and a 1 at the 10th position, right? But then if a word is not in the dictionary, the network cannot process it. But as there is many words in the human language, we can choose to restrict the dictionary, the number of words the network is going to know, and then remove all the unknown words, or replace them by a token that flags them unknown. And then, I don't know, the unknown token might be the unknown word, might be the last one in our dictionary. And it's going to be a word that represents all the words that are not in the said dictionary, basically. And then we have some functions to tokenize the text, but you've seen the theory last time. And here we create a class to load the data, basically, on the for the training of the network. So I don't know if you've trained neural networks before, but basically what you have is you need to have an object that is a data set, and this data set need to have some function that allows a data loader to take some batches of data from the data set to train the network. Because as I said in the presentation, when you calculate the error of a network, the error on a prediction, you don't actually make it on one prediction. You take a whole bunch of predictions and you calculate an average error on all these predictions. And this error tells the network how to update its weight to improve. So if you do it with only one prediction and then you calculate an error and you update all the weights of the network based on this one error, actually the error that you get is not super meaningful, because maybe, I don't know, you're classifying a sentence and maybe the sentence is not, is a bit weird, is not super relevant in the whole data set. And so updating all the weights of the network based on a single error, it's not super good. So that's why we're going to have a parameter in the training that is the batch length, and it's basically how many predictions the network is going to make before we calculate an average error and improve and update the weights. And so in our data set, basically, you have many reviews with many labels. With each review has a label. And the goal of the network is going to be to predict the right label, so positive or negative. But this class is going to help the data loader select, let's say, 20 reviews with the 20 labels, and calculate the error on the 20 reviews, and then update the weights. So this type of class needs to have like two specific functions. So 3 specific functions, but so this one is in most of the classes that in Python. It's when you create an object of these classes. So you're going to create a data set which has the structure of a IMDb data set. It has to initialize some internal objects, basically. So it basically, what does it do? for instance, you have to create a vocabulary based on the data set. So let's say you want your network to know 10,000 words. Well, when you create a data set, an INDB data set with specific data that you extracted from INDB, you have, let's say, 20,000 different words. If you restricted your vocabulary to 10,000, this initialization is going to create a dictionary of the 10,000 most common words, and it's going to remove the other 10,000 words of the vocabulary. So that's the initialization function, basically. And then for the data set that you create in PyTorch, you have to have two functions. One very easy one that returns the length of the data set, which is the number of examples in your data set. So here it would be the number of reviews, of movie reviews. And here the get item is a function that extracts one review. So one review in a textual form, the corresponding label of the review, positive or negative, and then the review as a sequence of tokens. And this function is going to be used by the data loader that is going to be plugged on the data set in order to extract batches of data. So this function only extracts one review with the label and the corresponding plain text. And this function is used in parallel, let's say, by the data loader to extract, let's say, 20 sentences at the same time with the 20 corresponding labels for the training of the network. Okay, here you have several parameters that you can tune. You can have fun with that. For instance, we have said that the number of words that the network is going to know is going to be 1,000. We can also restrict the maximum length of the review, because some reviews are going to be 5 words long, 3 words long. This movie sucks, for instance. And some other users are going to create whole paragraphs. And at some point, we might want to cut short the review and only input a truncated version of the review to the network. It would be mostly to reduce the calculation time, because processing a super long sentence takes more steps, and maybe it's useless. So you can also tune this parameter and see if the performances improve when you put the maximum length possible, and if the training time also becomes longer. Okay. Now, so as I said, I don't know if you have trained neural network, but anyway, that's good to remind you of that. When you train neural network, you have your original data set is going to be split into several data sets. So so there's going to be a data set to train the network. So that's the data set that we used in the presentation. And you've seen the training. So the model makes a prediction, and you can calculate an error of the prediction, and then you can update the weights of the network. And by doing so, the network learns something, and in the end, hopefully, it's meaningful. And then you have 2 other data sets, which are used for validation and test. So basically, when you do I have a sheet? No, I don't have this. That's sad. Anyway, when you have train your neural network, well, actually, while you train your neural network, you're not going to show it your data set only once. Maybe you're going to loop several times through the data set with your labels. And so you can do it. So 1 time would be training on all the data, and 2 times would be training twice on all the training data set, and so on. And at some point, you want to stop, and you want to find the ideal number of what we call epoch. So it's basically a loop through the whole training data set. We want to find the ideal number. So this ideal number is a parameter of the training. And so while training, we're going to have a validation data set on which we only calculate the error, but don't update the weight of the network. And we're going to see when this error start to increase, because when you train a network several times on the same data, it learns stuff, but at sometimes it starts to learn by heart the data set it is training on. And so that's what we call overfitting. And when it starts overfitting, it starts to lose the generalization capabilities that it has. And that's when the validation error, validation loss, is going to start to increase. So in the beginning, normally it should decrease. And at some point, when the network overfits, it's going to start to increase. And when it starts to increase, we need to stop the training. And that's going to fix the number of epochs that we need to train the network on. And once you have the number of epochs you're going to train your network on, you're going to merge the training and the validation data sets to have more data to train on. You're going to fix the number of epochs, and you're going to train your network looping through the training plus validation data set. And once you've done that, you can then test your network on a third data set that it has never seen, that wasn't used for tuning the parameters like the number of epoch. And this is going to give you the actual evaluation of the performance of your network. So the testing and the validation are different because as the validation is used to tune a parameter of the training, it's sort of a seen data set. And when we want to test, we really want to test on completely unseen data. Anyway, we have a function to split the data set into training, validation, and test. And you have a parameter that you can also tune to find the optimal one, which would be the percentage of your data that is going to be used for validation and test. And then the split is random according to these distributions. And then I've mentioned the data loader. So the data loader is basically, so the object already exists in PyTorch. And you just need to input it some PyTorch data set. So we've created a PyTorch data set above, right? I don't know where. Here, this one. And so if we create a version of a data set, then we can input it to a data loader, just like that. It's going to create a good data loader that is compatible with our network. Two things. So the batch size here is going to be the number of prediction you make to calculate an average error and to update the weights of your network. So you can also modify this parameter if you like. And then you have a function. Well, let's not dive into the details of the collect function. So here you have like the hidden part of my presentation, but I can go quickly over it. You have the standard recurrent neural network here. So you can see that this pipeline here is the pipeline for the hidden state, and this pipeline here is the pipeline for the words in your sentence, right? In a recurrent neural network. So we can see that we have seen that with the standard structure, we're going to have problem with the long sentences. And so to deal with the long sentences, we can use what is called LSTM. So you don't really have to understand it because actually in PyTorch, you can basically create the class and then just tune some parameters, but the LSTM is going to exist by itself, sort of. But anyway, the specific thing of the LSTM is that it has two pipelines. So it's two hidden pipelines. So you still have the pipeline to input new words, right? But you also have two pipelines of hidden states. One, let's say, for long-term memory and one for short-term memory. So one is basically used to capture the local meaning of your current word. So it only remembers the few previous words, just like the RNN basically. And the long one here is going to be used to capture more long-term dependencies. So basically the words in the beginning of the sentence. And then the details are not super relevant here, but that's the principle. And so you can see a little animation here, right? With the new words getting inputted. and then the information getting passed on. Here we have an engineering function. Let's say that if the sequence, so we have a max length of the sequence, which is 220. Some sequences are going to be smaller than that, and so we're going to just pad them with meaningless tokens, so that each sentence has sort of a fixed length, even though like most of the sentence can be composed of padding tokens. So we're going to directly create a LSTM classifier, LSTM-based classifier. So this function here is the PyTorch function to create an LSTM. So you don't have to understand how it's done to create the LSTM. So you just call the library and input the right parameters. So you have several parameters: the size of the hidden layer, the number of layers, because you can actually stack LSTMs. I'm not going to explain how you do it, but anyway, PyTorch allows you to do it. So you can tune that parameter if you like. And then the dimension of the embedding. So that would be the dimension of the sort of Word2Vec-like vectors that are inputted to the LSTM. Okay, and then well, here when you initialize an LSTM, you have different parameters. Anyway, if you have questions about these parameters, I can answer them. And basically, when you create a neural network in PyTorch, so apart from the initialization function, which is like the initialization function of the data set, for instance, you have a very important function, which is the forward function. And the forward function is basically the function that takes an input and makes a prediction. So it's the whole pipeline from an input, a review, from a prediction. Is it positive or is it negative? So you can see that you have an input, and you can create the embedding for the words of the input, and then you can apply so you have a function to apply the recurrent neural network to the review, and then you have some classification parts. So it's dense layers, so fully connected layers that are going to make the classification for the review. Anyway. I've given you a little homework if you like. It's to create similar, so basically you can almost copy paste it, but instead of using an LSTM here, you can use RNN or a gated recurrent unit or any recurrent network that you can find in the NN library of PyTorch. Here you have the documentation of the library. So you have the LSTM, and you have torch.nn that basically, so PyTorch allows you to create many kinds of neural network, right? And you can create recurrent neural network. So I mean, you can read the documentation if you're a geek. And so you have the documentation for the recurrent neural network, for the gated recurrent unit. And then you have a function to train the model. So here it's a function to train on the whole data set, right? To train one epoch. And then you have a function to calculate the validation error after the epoch. So that's the training that I've explained before. And yeah. You can have several parameters for your LSTM. So the dimension of the embedding, the size of the hidden vector, and then you have the learning rate, which is also a parameter of the, let's say, the steps you make, the rate at which you change the weights when you make an error. So roughly, the higher it is, the more you're going to change your weight given a specific error, sort of. And that's a parameter that you can tune as well. I mean, you can have fun with this and try to create your own LSTM and see if you can beat me. All right, and here you have a summary of the full classifier that you have. So you have an LSTM inside, but you also have some. So the LSTM is for basically the encoding. It creates a vector to represent the review, the sentence, I mean the paragraph, and then you have a classifier on top of it, which is linear layers that are going to use the embedding to calculate whether the review is positive or negative. Then you need also to tell the network how you're going to calculate the error, and so I'm going to explain that a bit later. And also you have something that basically is going to optimize the way you update the weight. So it's called an optimizer, and you need that for a neural network. So basically the optimizer looks at the error that the network has made, how the weight have changed, in order to calculate the way the weight needs to change given the errors, basically. But everything's automatic, right? And so for the cross entropy loss, it's the standard loss for classification. So it's basically when you have a classification, you have several classes, right? Here it's two. You have either positive or negative. This loss basically calculates how accurate you were at predicting the category. Because when you predict a category, you're going to have a probability. So for two categories, you're going to have a probability that the sentence belongs to the first category and a probability that it belongs to the second. And the cross entropy is basically, it knows the right answer and calculates the difference between the distribution that you calculated and the actual distribution, which is always a 0 at the wrong category and the 1 at the right one. Anyway, you can also check that, but I think you're going to do, or you have done visual classification in your classes, and so you're going to use, or you have used, the cross entropy loss. Okay, and then here it's a loop on the epochs. So you have parameters that is the number of epochs that you normally calculate with the validation loss. When the validation loss starts to increase, you know the number, the epoch number, and you stop there. And so for a loop on all the epochs, you're going to use the function to train the data set and to validate, and then it displays the evolution of the loss, of the train loss and the validation loss. And so it decreases, which is great because the loss is the error, right? So you want the error to be minimal. Normally, what we should do is we should merge the training data set and the validation data set. You can actually do it if you want. You merge the two data sets and you train on both the data set, not only on the train. And it should give you better results on the test data set. So you should try that. And here we evaluate the network on the test data set. So we have several ways of measuring the accuracy of the network. So you have I don't know why. So basically you have the accuracy. So when it makes a prediction, 84% of the time it's right, let's say. And then you have some averages, right? And so let's say the weighted average would be that if you have more of a class than of another, let's say you have only 10% good review and 90% bad reviews, then the network is going to be inclined to predict, like all the time, bad reviews, and can achieve with that 90% accuracy, right? If you have 90% bad review, and it always predicts that the review is bad. So you could want, so here it's not the case, but I'm displaying it anyway. You could want, for instance, to give more importance to predicting a positive review, because there are less positive review, and so you want to make it balanced artificially, and so you can measure different types of accuracy depending on the reportation of the labels, basically. And then you have definitions of the scores that here, so you can read that, and you can, yeah, anyway. And you can, so just so you know, the higher the better, right? You want to be as close to 1 as possible. So if you beat me, you need to be closer to 1 than me in one of the metrics here, right? Okay. And here we can see some actual examples of classification. So in my case, we are lucky because the network has made no error. So you can see some reviews, and then you can see the labels predicted by the network and the actual labels. So apparently it was right. Let's say if the actual label is the actual label. You must see it positive, right? This one doesn't seem so positive, but apparently the label is positive anyways. All right, so this was the classification network. Any question here so far? No. Okay. Well, let's go to part 2 then. Okay. So here we're gonna stay in the movie domain. We're gonna download some movie plots. We're gonna train a network to finish the movie plots. We're gonna input the network the beginning of movie plots, and it's gonna have to finish the movie plots to guess the end, basically. So obviously it's gonna be lame. What we should do in that case would be we would have 2 options to be actually good at generating movie plots. Either we would need like a lot of movie plots, but like all the movie plots that exist in the world, basically, and train the network on that, and we're super good at like generating movie plots. Or, and that would be a more probable solution, we would need to train a network on like a general language data set. So let's say all the articles in Wikipedia in English. Then the language would be able to understand how the structure of the language works. So it's going to be able to guess which word follow which word, and how grammar works, and what is incorrect and correct. Statistically understand, but still understand. And once it understands language, we would have to fine-tune it, so which means freeze most of the weights of the network and only allow the network to change some of its weights. We would fine-tune it on a movie plots database so that it doesn't have to understand language from the movie plots, right? So first we need to make it understand language and then fine-tune it so that it's specialized in movie plot generation. But we don't have the data set and we don't have the computational power to do the pre-training. So we're just gonna train a movie plot generator on a small data set, and it's gonna be quite lame. Anyway, we still import some libraries. We are still gonna use PyTorch. And then we're gonna use a file of movie plots So it's really, really small. Actually, one really good thing that you could do to improve this notebook would be to find a bigger data set of movie plots and generate better movie plots according to that. I'm telling you that not because I want you to do homeworks randomly, but because probably you're going to be evaluated. At least last time it was like that. You're probably going to be evaluated on the improvement of a notebook. So I'm giving you ideas so that you don't have to find find the ideas yourself on simple things to do to improve that kind of notebook. Yeah, okay. So feel free to write it down. Okay, so we can see here an example of a movie plot. So a movie plot about Barry. I don't know. Maybe some of you know the movie. We can also remove some weird character that we don't want to have to deal with, right? So we are using the library RE, I don't know how it's said, to remove some weird words. Okay. And then we're going to create a data loader that is going to extract sequences of length 5 from these movie plots. So basically, the goal of the movie plot would be, the goal of the network would be to predict each time the following word, right? So so you can divide your plots in sequences of size 5, right? And if you look at two consecutive vectors, you can note that the future of how to put it, the word that you have to predict from the first vector is actually the same at the same position in the second vector. So when you input good to your network, the network has to predict morning. When you input morning, it has to predict this. When you input this, it has to predict is Mr. and Mr. Prabhakar. Anyway, so that means that we can use these vectors to create basically some inputs and some labels, sort of like the prediction the network has to make. Anyway, so we have 500 movie plots. If we divide them in fixed length sequences, we have this number of sequences, and you can see that the sequences are ordered according to the movie plots, right? And so you have the as I said, you have the inputs and the labels, sort of like the past and the future. So from the past, the network has to guess the future. Here we tokenize manually the words. And anyway, so you've seen that in the previous notebook normally. So we are just recreating what PyTorch can do automatically normally, right? Here we can get some batches. So you have a batch size, and you can extract batch from your sentences to make the predictions. And here you create the LSTM, so you can see that it still has the initialization function with the same kind of parameters. We use an LSTM, so you might want to use a gated recurrent unit or a recurrent neural network or something else. And you also have the forward function, which is the function that, given an input, predicts the output. Okay. And so basically, that's the function that predicts the next words of the sentence. All right. And so we create an actual network with the default parameters that I have written here, right? That's the default parameters of the network, and we put it on the GPU with the CUDA. Then we have a function to train. So we have the optimizer, as I told you. You have a cross entropy loss, which should be a classification loss over the dictionary. You have to predict the next word. So that's the classification task, right? You have a dictionary and you have to predict the right word in the dictionary. And so each word is basically a class. So it's a classification task. and then you can, for each epoch, you can loop through all the batches and predict the next words, and then calculate the error and improve the network. All right, so we do a certain number of epochs, right, with a batch size of 32. You can tune that, and then the network is trained. And once we have trained the network, we want a function to predict a function that uses the network to predict the next word given the beginning of a sentence. So that's the function here. I'm not going to detail it because it's not super interesting. And then you have a function that we call sample, and that's going to use this next word prediction, but that's going to loop over the next word prediction in order to create a full sentence and a full plot, maybe. And yep, that's it. And so, as I said before, normally for a good network, we would have it generate its own end token, right? So it would generate words until it reaches the end token and say, okay, my plot is finished. But that's a bit complicated to engineer that right now. So we're just going to do it simply and have a parameter of the sample function that gives us the size of the plot. So if you do a sample without any prime, so sentence beginning, it's going to generate the full sentence. Well, you can see that it's not a great plot, to say the least, but it's still kind of grammatically sort of okay, it seems. So it means that given very little data, the network was sort of able to capture some grammatical structure. So in the second example here, I'm generating a plot with a prime. So the prime is Batman is. So that's going to be a movie about Batman. And we can see that the plot that the network generates is a bit less good than the previous one grammatically. Yep. So that's basically it. So it's kind of a shitty network, but still it generates words, right? So it does the job, let's say. And so you can try to find if you put a longer sentence, maybe the next few words are going to be okay, or maybe not. You can try that if you want to have fun. And sometimes also the output is fun. Yeah. So I've detailed some exercises that you can do on this notebook if you want to, well, just improve or improve yourself, or just for the final exam, let's say. I have not written everything, so I hope you took note if you're going to choose that notebook. And if you don't have any question, we're a bit early, but we're done. Was it clear? Yeah. Vous n'avez pas fait beaucoup de Python avant, hein? Pas du tout, super.
On a fait là durant ces cours-là.
Ok.
Du coup,
ça va être un peu compliqué. Mais, je vais le dire en anglais. Don't hesitate to send me an email if you have trouble with Python stuff. Well, usually I try to find the time to reply, and from experience, it seems that the best grades are from the student that asked questions, because, well, they can then go further because they are not limited by some very, like, some Python skill that are not related to neural network. Right? So if you do choose to use this notebook, you can send me emails and I'll try to reply. Okay. And that's it. So what's happening on Zoom? Not much. Okay, well, if you don't have any question on Zoom, I'll finish the presentation here. And goodbye.
Thank you. Bye.